Okay, let's do this example from assignment 3. We're doing problem 3. So we start off by drawing the yield line pattern. And my general rule when drawing them is that I start at the edges of one of the supports. And then I move towards the free edge in this case, since we have a free edge. This edge right here. Yeah, we move towards the free edge since the free end can't resist a moment or a force. So yeah, yield lines go like that. And then we separate it into regions, and I also labeled out the dimensions using the geometry of the shape. And yeah, we know that region A is equal to region D and B is equal to C. So we only have to solve for 2 technically. So we start, one more thing is we have 2 fixed edges here, and whenever you have a fixed edge, you need to consider both positive and negative moments. So yeah, we just draw like a dashed line along the edge to indicate that. And the calculation is gonna involve adding both positive and negative moments. But we'll start with element A, which is along a pinned axis, so we only have m equals m positive here. Then I wrote down my internal work done equation, ml theta, then L. Definition of L is the length of the projected yield line onto the axis of rotation. And so this basically means we have this yield line here on region A, we project it onto this axis. And so whatever this distance is, that's our L. So in that case, it's L over 3 plus L over 3, which is 2L over 3. Then we have our rotation for region A. And for this part, I go back to his notes where he mentioned which length to use. And so he mentions here, the length is measured perpendicular to the axis of rotation to the point of maximum deflection of that region. Means is that we start at the support and we go towards the yield line, or start at the yield line, go towards the support. But anyways, this is the distance that we're using. And we want maximum deflection. And obviously, this is the maximum point based on the image and the yield lines that we have. And so to help myself picture it better, I just got this 3D triangle off the internet. Yeah, so when we're calculating theta, it's obviously opposite over adjacent. Yeah, so it's deflecting into the paper. So if you imagine it into the paper, it's gonna go like that or something, right? This is your deflection distance. And then this dotted line here is the x that we have. And we have your theta. So that's how I picture it. So in this case, your theta would just be your deflection over the x distance, and the x distance in region A is just L over 3. We can line up the things with that. L over 3. And so, yeah, it would just be m positive 2L over 3 times L over 3, which eventually just cancels out to being that. Now let's move on to element B. And now for element B, we have a fixed support here. So we need to consider both m positive and m negative. This is always the case for a fixed support. So let's start off with m positive. And for this case, L, your projected length onto the axis of rotation is These are the yield lines for that region. And if we project it onto this axis, we see that it covers the entire length here, which is L. So it would just be L. Then deflection here, again, when finding that length that we need in the denominator of the equation, we start off, we want maximum deflection, by the way, so I'm starting in the middle because that's what gives you the largest length. Yeah, start here to your support. So now we're using this distance. Before, the support was on the Y, now it's on the X. So perpendicular is that for region B. And that distance is, again, L over 3 plus L over 3. So 2L over 3. So we have our deflection over 2L over 3. Yeah, that makes sense. Then you can also imagine it going this way. 2L over 3. You have theta, then your deflection. It's a really bad drawing, but you get the point. Yeah, when you're drawing it, imagine it going into the paper. Then, what's the positive? Internal work done by B positive equals M positive times L times 2L over 3. Okay, now we have to consider the negative case, but the negative case is nothing different. For this one, yeah, all we do is just make it M negative. But I think, wait, in the problem they said that, yeah, they said the negative reinforcement is that, so I should stop using M negative. It's that they're just using another symbol. And then everything else is the same, by the way, like L, theta, it's all the same. L, the only thing that changes is the moment symbol, that's it. And then we just add the two up to get your total internal work done at B. Here, let me simplify these a bit more. They look kind of messy right now. This becomes, yeah, just I'm gonna get rid of the plus here because we're already using this ML over 2L. And then the negative is the same thing, except we have something added to it. Then when you add the two up, you just get 3. 1 plus, yeah. That's your final answer for that. And then, yeah, total internal work done at B is just, I mean, not B, just done in general, is 2 times A plus 2 times what's done at B, because we have 2 of each shape. Yeah, that's your total internal work done. Now we need to calculate external work done, which is just the formula, N times displacement, which is just area times the load times your average displacement And so when we're calculating external work done, there's two types of questions that he asks. It can either be isotropically reinforced or orthotropically reinforced. So when it's orthotropically reinforced, that means that the moment capacity is different in the x and y directions. But it's isotropically here, so we don't have to worry about that. So we can just calculate the entire area of this. Yeah, and it just makes it way easier. So in this case, this is basically a huge square with this corner cut out of it. So to get the area, I'm just gonna do L times L, area of the entire square, and just subtract this part out. So in that case, the area is just L squared, minus L over 2 times 2L over 3 times 2L over 3. It's not L over 2, I meant half, because this thing is a triangle, so half, 12 over 3, 12 over 3. That's the formula. Yeah, so that's for the area, and then the load is just W. Then for average displacement, go back to the notes. Down here, I think. Yeah, here. We can simplify it. So it's half for rectangles and then 1/3 for triangles. And in our case here, we just have a bunch of triangles. 4 triangles. So we use delta over 3. Then after solving for that, this part you just get 7 over 9 L squared times W times delta over 3. And so your total extra work done is just 7 over 27 WL squared over delta. Yeah, and that's your final answer. That's what they're asking for.